Well, good morning, afternoon, evening, wherever you are, whatever time it is that you're going to watch this. What we're going to look at today is this pre-lab for the mass mold relationship laboratory that we do. And our first question says, write a balanced equation for the reaction that occurs when aqueous solutions of barium chloride and silver nitrate are mixed. Okay, well, the strategy for solving this is that we first need to figure out formula for things like barium nitrate, or excuse me, silver nitrate and barium chloride. So use that handy dandy cheat sheet we all refer to in chemistry as the periodic table. And if we look up barium, Ba, we'll see that it has a +2 charge on it. And if we look up chlorine, the other side of barium chloride, we see that it has a -1 charge on it. Well, those two things won't go together very well. That is to say, they would go together and not be very stable, because for it to be stable, it has to achieve a net zero charge. So what if I doubled up the chlorine? That would give me two negatives to go along with the two positive from the barium. So I would write that formula, again, always starting with the cation, as BaCl2. Now for the silver nitrate, silver is one of those funny ones in our periodic table where the name holds over from the older Latin and French words argent, which means silver. And if I look it up, it has a +1 charge on it. And the nitrate doesn't actually appear on the periodic table per se. We can find nitrogen and we can find oxygen, but it's real easy for us to think of this nitrate as almost like an element of itself. These polyatomics, as they are called, behave very, very much like an element. And there's plenty of places to find information on these polyatomics. You may have a list of polyatomics, or I often refer to the solubility rules, and the most used polyatomics appear there, like nitrate, for example. So if I look up this NO3, I'll find that it has a -1 charge. So these two, when I put them together in order to form a stable compound, net zero charge, they would only have to go together as AgNO3, kind of a 1-to-1 ratio. Make sure that's an A, not an H. There we go. Okay, so what would happen if we put these two things together? We are told that they are aqueous, so I can put a little AQ in parentheses, kind of small and behind each of these. And that's important because what that tells us is for aqueous solutions of ionic compounds like barium chloride, you don't really think of them as having barium chloride in the solution. It's easy for us to think of them instead as having a lot of barium ions, a lot of chlorine ions, some nitrates, and some silver ions. Okay, so if we put all those things together in the same solution, and now they're free to interact and maybe join up with something they wouldn't otherwise have. What happens if we take this positively charged barium and we put it together with a negatively charged nitrate? Well, if that is a potential product, I have to remember that my barium has a +2 charge on it. Each nitrate has a -1 charge on it. So I'd have to double up that nitrate, wouldn't I? Okay, so let's again think of the nitrate as an element almost all to itself. If I want to double it up, I have to make sure I double up the entire thing. And I can show that with these parentheses. Okay, what else does that leave us? It leaves us the silver and the chlorine. Well, in order to combine those, the silver has a +1, the chlorine has a -1, so they simply would go together 1-to-1, AgCl, and achieve that good stable net zero charge that we always try to. Okay, so what kind of states are these going to be in? I'll refer to those solubility rules, and I can remember one of the easy ones to remember is all nitrates are soluble all the time. And so since they're soluble, they dissolve in water, we know that one's going to be aqueous. What about the silver chloride? If I look up the chlorides, I'll find that silver chloride does not dissolve in water. In other words, it forms solids, what we might see as precipitates in the lab. And so we'll put a little S behind that one. Okay, the last step in balancing this equation, now that all of our reactants and our products are good, stable, net zero charge. Now we have to make sure that the same number of elements of each type are on the left and on the right, on the reactants and on the products. So we start off with one barium, and we have one barium, that's fine. We have two chlorines. Uh-oh, we only have one chlorine over here. Now I can't simply double up the chlorine. If I want two chlorines on my product side, I have to double up the whole thing. So I'm going to put a large 2 in front of the silver chloride. Okay, well that has repercussions because now I have two silvers on my products side, which means I also have to have two silvers on the reactants side. Let's put a 2 in front of there, and bear in mind, of course, that I'm doubling this entire thing when I do that. So that means I now have two nitrates on my reactant side. But that works out great because on my product side, we've already figured out that we have two nitrates. So just to be clear, let's double check everything again. Barium, barium. Two chlorines, two chlorines. Two silver, and finally two nitrates and two nitrates. So now we have a balanced chemical reaction for barium chloride and silver nitrate. All right, let's take a look at the next question. And it wants us to predict the mole ratio of barium chloride to silver chloride for the equation. Okay, well, this is going to require us to do a little bit of manipulation from words to mathematics. When I see BaCl2 to AgCl, if I want to think of that in terms of mathematics or a ratio, I would represent that like a fraction. So whatever is listed first, let's put that in our numerator. And then whatever's listed second in our denominator. So in order to represent this as a mathematical ratio, I want barium chloride to silver chloride. Well, I just balanced this equation up here, and what is that ratio? It's barium chloride. When there's nothing in front of it, we can assume that that's a 1. And silver chloride, where we're at over here, that has a 2 on it. So that ratio then is 1 barium chloride over, or for each, 2 silver chloride, a ratio of 1 to 2. Okay, that satisfies the second question. Let's take a look at the third and final question on this pre-lab. It says, if an experiment with 10.2 grams of barium chloride produced 14.5 grams of silver chloride, calculate the experimental mole ratio of silver chloride to barium chloride. Okay, this one is interesting because we're given grams, but they want the answer in a molar ratio. All right, so we're going to go back to the periodic table because that wonderful cheat sheet has all kinds of equivalence statements in it regarding mass and mole. Okay, for example, if I look up barium, I find that its molar mass, or its molecular weight, or actually its elemental weight, because we're talking about an element here, is 137.327, and that, of course, is grams per mole. All right, so 1 mole of barium has a mass of 137.327 grams. Okay, so I can use this with all of the elements to create what we know as a molar mass, a molecular mass. So for barium, for example, I have barium at 137. I also have chlorine at, let's see, my weight for chlorine, the periodic table gives me as 453, again, grams per mole. But I remember that I need 2 of those. So that comes out to 70.906. And from the barium, I only need one of those, so I have 137.327. If I add those up, I get 208.233 grams of barium chloride for each mole of barium chloride. Okay, I'm going to circle that because we're going to need that in just a minute. All right, I can do the same thing for my silver chloride. I have silver and I have chlorine. The elemental weight for silver is 107.863, and chlorine, of course, we just used at 35.453. I only need one of each of those. I don't need to double or triple anything up. And when I add them together, I get 143.316. And I remember that what this number means is it's grams of silver chloride for each mole of silver chloride. All right, I'm going to circle that one. Now, the original problem said that we started out with 10.2 grams of barium chloride, and I want to convert that into a number of moles of barium chloride. In order to do that, I can use this equivalence statement that I just figured out. Now remember that when I have this, I can also use it inverted because these things are the same. Okay, so I could use this as 1 mole of barium chloride for each 208 grams of the substance. In fact, if I'm starting off with grams and I want an answer in moles over here, I need to put my grams underneath this next part. So I'm going to put 1 mole of barium chloride in the numerator and 208.233 grams of barium chloride in the denominator. When I do this calculation, I've done this calculation, here we go, I get an answer of 0.0489836 moles of barium chloride. Remember that what I have over here, we can always think of a number by itself as being over 1, so it'd be in the numerator, and whatever's in the denominator that is like will more or less cancel each other out. So the only unit I have left then is moles barium chloride. All right, let's do the same thing with the silver chloride. We ended up with 14.2 grams of silver chloride, and I calculated the molar mass of that substance as 143.316 grams per mole. Again, I'm starting out with grams and I want to end up with moles, so let's put the mole on top. And then our mass, 143.316 grams of silver chloride. Again, the grams silver chloride will cancel, and that gives me an answer of 0.0101175 moles of silver chloride. Now, in both of these cases, you'll notice that I continued the answer way out past the maybe 3 significant figures that we really should, and I'm doing that because this is just an intermediate answer that we're going to use to complete this calculation. The final answer we're asked to find is a molecular ratio of these two things. And so I'm going to revisit the question here to make sure I've got it correct. And it wants the mole ratio of silver chloride to barium chloride. In other words, remember what we did up here, we want to put this one in the numerator, the top part of the fractional ratio, and this one in the bottom part of the denominator of that ratio. All right, so we're going to put silver chloride on top, and barium chloride on the bottom. All right, we had 0.0101175 mole of silver chloride, and we're going to divide that by 0.0489836 mole of barium chloride. And when I plug that into my calculator, I get this big long answer of 1.9307033 moles of silver chloride over 1 mole of barium chloride. All right, now that we have this experimental ratio in hand, we can satisfy the question more accurately, I should say as accurately as we're allowed to, by going back and looking at this initial data we were given to 3 significant figures. So I would actually write my ratio as 1.93, right, moles of silver chloride for each mole of barium chloride. That's my final answer for the third question, and it does satisfy the question. Thanks, and I hope this helps you.